in many reputed international conferences also. He has expertise in machine learning, support vector machines, extreme learning machines, wireless sensor networks, and IoT. It is a great honor and privilege to have you here, sir, for this expert session. I once again welcome you, and now I request you to interact with the students and faculty present over here. Over to you, sir. Thank you.
Thank you, Lipika ma'am. Thank you for this nice and long introduction. Actually, let me tell you, ask you first whether my screen is visible or not.
Yes, sir, your screen is visible.
Okay,
right now, I can see your team's screen. Yeah.
Okay, thank you. So, without going into a lot of other things, let me tell you, I am faculty at NIT Kurukshetra from 2013, and many times I have taught this subject, machine learning, and people actually shy away from this subject because there is a lot of mathematics involved in this particular subject. So let me try to give you an overview and specific ideas about machine learning. So I'll try to start machine learning in the sense that what it is, what is the role of this particular thing in the whole world. So let's talk about machine learning. So we are looking for the place where this machine learning is actually required or works. Let's try to see in this real world what are the things, how this real world actually composed of. Have certain nouns, certain states of the objects, and we define with their descriptions. So soon we will see as an example also, but mostly we see nouns here and there. So camera, desktop, bottle, and a lot of other things. And then we have certain thing that actually works. It's a verb, action, which manipulates the noun, changes the states, and that's where actually the things go into action, right? So let's just look at this particular noun called CPU, and people define it in various ways. Let's try to define ourselves. So describing this particular thing, let us suppose with these 4 attributes. Are these attributes enough for something? Means for some task or something. So maybe these are the attributes. Actually, they looks like they are important if I want to ship it somewhere else. So if I go to the post office and want to ship it, or courier office and want to ship it, they may want to know how much volume it may require, what kind of volume it may require, and what's the weight of it. But if I want to buy it, I may require something else. Maybe the number of hard disks, the number of CPUs, the types of hard disk, and all. Right? All these attributes are actually required to buy it. So that's one question. If you ask this question from yourself, if you have any answers, you can share with me. Do you think that all such attributes are required while buying or while trying to buy this particular CPU? Maybe you will also believe that ICs are not the right thing. I am not interested in knowing the number of ICs used. So that's where we can understand this thing, that everything can be described by certain attributes, certain features. So these are kind of features: height, width, weight, number of hard disks, what type of hard disk. So these are kind of features, and these features are required based upon the question that you want to ask. If you want to ask something else, maybe you want to propose a price on this CPU, then you may not be interested in the color. You may not be interested in the height. You may be interested in something else. So it actually depends on the question, how you want to describe a particular object. And this description is actually the most important idea when you consider, when you think about machine learning. Why? So let's try to understand one more question. When do we need IDs like MAC addresses or chess number? So do we need them? So the answer is like we need them when we want to do some kind of a network business, or we want to identify each and every uh, component or the device on the network individually. So then only we need to know whether there is a MAC address, whether this MAC address is different from the other MAC address, something like that. So all those things are required. So in one question or in maybe another question, these things or these different attributes are required in different ways. So not in all questions all the attributes are required, but depending on the question, you choose your attributes, you describe the things in that way, and accordingly you try to work with the problem. And what about actions? So actions are like selling, upgrading some component, changing some component, and connecting them, and so on and so forth. But in this particular presentation, in this particular work, in machine learning specifically, we are not much interested in actions, as long as actions can be put up in the form of nouns or the states. Let me tell you what I mean to say by this particular thing. When I want to look at the machine learning, the problems that machine learning addresses are based on the questions whether something is similar or something is different. So based on the description, because you have a certain question in your mind, so you write the description on that particular way or based on the problem, and based on that particular description, you want to identify whether something is similar or something is different. Whether this CPU has 8 cores or 4 cores or 2 cores or single core. So the difference is actually something that you are looking for. The similarity that is you are looking for. So similarity and dissimilarity are the measure of something. If you take one thing, then you can measure another thing. So if you have similarity, you can also calculate dissimilarity in some way, a function of similarity, right? So in machine learning, most of the questions are actually related to similarity and dissimilarity. And if you are asking any question, and if you can break down the question into finding the similarity and dissimilarity, then machine learning can come into picture. That's the place where machine learning works. Now, the two important questions come into the picture, like how many descriptional attributes should be taken? And definitely the answer is we cannot say it for sure, but yes, if they are too less, then they may not provide sufficient information to solve a particular problem. But if they are too much, then the thing becomes too complex to analyze, right? So what kind of descriptional attributes we want? Those attributes that are actually required for our problem. For example, in the last case that we have seen CPU, if I want to identify a CPU, a price of CPU, then possibly the number of cores of CPU is one of the most important attributes. Number of hard disk and the size of hard disk can also be the important attribute. But the color or the case size may not be that important. right? So we are looking for the right attributes that are required to do our job. But there are certain challenges with when we are working or we are selecting the features. We are having a lot of cases, we are having a lot of issues with them. One of them is ethical issue. There are cases like granting bail to prisoner. So there is a particular case in US. They have implemented a AI assisted software which actually allows or which actually predicts whether what is the risk of granting bail to a prisoner. Now, what happened uh, in case of this particular problem, that the data itself is generated by the people who themselves are biased towards blacks and whites. So if the data is itself biased, then the data and the learning from that particular data, because you have taken some description, in that description you are defining that it is black, some person is black, and then you are describing its crime. And since the crime is reported by the society, which is generally biased against black people, then they will write the things in their way. And that is affected, or that is the notion is reflected in the data. And the same data is used to predict whether to give the prisoner a bail or not. And the same thing happens with in case of bank loans. Again, in this case is also from US, and people are saying that if you are going for a bank loan and this AI is actually taking over, and people are actually uh, feeding the documents. And this is the document about the description of the loan applier and the loan amount, whether to sanction it or not. That's the data, previous data that we have. So what happened is that many times this AI assisted thing does not work positively with the women. The reason is, again, the data that is generated by the people is already biased against the women. And if they are biased, definitely the learned model will also be biased. So whenever we want to actually select the features, we have to be very careful about these ethical issues. Another issue is dimension. How many attributes I can actually take care? So we have already seen some kind of intuition from the previous slides, but let's try to look more things about this dimension. First of all, let us consider 4 data points, A, B, C, D, and let's try to understand how many different classes or how many different classifications are possible. So let us suppose I have 2 different classes. So these 4 data samples can be classified or can be put into one or the other class, positive class or the negative class. So could be this arrangement is possible. So all of them are positive in the positive class, none of them in the negative class, or possibly this arrangement could be possible. So A can be in the negative class and rest of them in the positive class. So every class or every data sample can be put into either +1 class or -1 class. So A can be put into 2 different classes. B can also be independently put into 2 different classes. C can also be put into 2 different classes independently, and similarly with D. So therefore, we have all such things, and these all such things makes 16 possible classifications, right? So when I see that, let us try to observe one more thing, that you can see that this new classification is exactly opposite to this particular classification. So this classification is just reversed. So you are saying that this is positive, all positive, this is all negative. So if I take a kind of a line and want to say, okay, left of this line is one class, right of this line will be positive class, or left of this line is positive class and right of this line will be negative class, then I can say that we can work with 8 classifiers. So, the sides of the line, you can always choose which side you want to be keep it positive and which side you want to keep it as negative. So there are 8 linear classifiers may be required to solve all those problems, all these different problems, right? Okay, so but can these dimensions, if I increase the dimensions, because we are talking about dimensions only, if we increase the dimensions, do they help in classification? Let's see with one-dimensional case. So this is the one-dimensional case where I have this linear classifier on the left-hand side. So all of these data points are classified into positive class or maybe the negative class, whatever you want to choose. But this could be another one. This could be another one, and this could be another one, right? So you can see that these are the possible classifications. And if you consider that the right of this line will be all positive, then these are 4. And again, if you consider right of this line is negative, then again 4. So almost 8 classifiers we have. We have already seen 8 classifications possible. We have already seen that there could be 16 possible classifications, right? And out of those, we can only support 8 classifications in case of a linearly, or if in case of points distributed in one dimension. So this is only one dimension. All the data points are kept on a line. So all these data points are one line. So either this point be here, either this classifier can be here, or can be here, or can be here, or can be here. So the left of this, or the less than this and greater than this, less than this and greater than this, less than this and greater than this. So this is the possible classification, right? But let us try to see the same thing in case of two-dimensional space. Now, if you have a two-dimensional space, you have these much of classifiers. Again, you can choose whether which side of the classifier you want to choose, positive or negative. So if you see, these are the classifiers that you can actually have. Here you have C in the positive and rest of the A, B, D are in the negative class, and others in this particular case, B is on one side and others on the other side, D in one side and others on the other side, and so on and so forth. So if you look at it, we have 1, 2, 3, 4, 5, 6, 7 classifiers we have. And if you choose it, one to be positive, another to be negative, one to be negative, another to be positive, there are still 14 possible classifications that we can cover. So here we could have covered only 8 classifiers, 8 classifications. Here we are covering 14 classifications. Still, 2 classifications are left. What are they? Can we classify AD in one class with just one line? I have to draw just one line, and AD in one particular class and BC should be another particular class. There is no possibility. There is no possibility that we can do that, at least with the 2D. So definitely we can see that if we grow our dimensions, then it helps in classification. It gives more power to the classifier. But there are some other problems with the dimensions. Let's try to see them. There is something called curse of dimensionality. Let me read this particular idea from Wikipedia for you. And it says that The common theme of these problems is that when dimensionality increases, the volume of space increases so fast that the available data becomes sparse. Now, let's try to understand this line. The volume of the space increases so fast that available data becomes sparse. I'll take you to the uh, spreadsheet. So this is a square, or you can assume that a particular box is there of 2 dimensions. So if you are in one dimension object, if you are considering one dimensional object, it is just one line of 2 units. If you are considering 2 dimensional object, then it is a square of 2 unit side. If it is 3 dimensional, it is a cuboid of 2 dimensions or 2 units of each side. So similarly, you have n-dimensional object. So if you have n-dimensional object, then this is the volume that this hypercube will take. So if there is only one line, it's one-dimensional, so it is only 2 units. If it's 2 dimensional, 2 cross 2, 2 times 2 becomes 4 units. 4 units, that's the volume of the hypercube. Again, if you go for cube, it becomes the volume, that is 8, and so on and so forth. Now consider this circle or the sphere that is enclosed in this particular cube. Why I am talking about this sphere? Because this sphere is specific in the sense that it says that the distance of all the points within this sphere is at most 1. Within this sphere, the distance of the points from origin is at most 1. Right? So that's the sphere. So I am actually made a sphere that is enclosed in that hypercube, and this is hypersphere. So if you are talking about a 3-dimensional space, it is a sphere. If you are talking about 2-dimensional space, it's a circle, and so on and so forth. Now look at this. This is the volume that this sphere actually encloses. And you can notice that the volume of the sphere is actually decreasing, while the volume of the hypercube is actually increasing. So I hope this actually helps you understand this idea. Okay. This particular thing actually let us know the volume of the space increases so fast that the available data becomes sparse, which means that the data within the circle will be very, very small. Very low quantity of data will be within the sphere. Mostly the data will be at the edges of this cube. And because of this, the distance between the data points will be large. And if you take the distance between because distance is the major issue while calculating the similarity. Whenever we are looking for the similarity or the dissimilarity, we are looking for the distance in certain way. So we will talk about that also. What is the distance in case of different issues? But we are looking for the distance. For example, I am connected to you through a network. So the distance in certain way is low between me and you. While if I take the distance between me and Obama, it may be very large, right? So this distance is geographical distance, but the distance between me and you is still very large. But yes, it is in one particular dimension. Because of one particular dimension, it has decreased to a very low value. So let us see. Because of this particular idea, because the idea that the data becomes sparse in high dimensional space, the distance between the data points will be very large, And when the distance between the data points is large, then it is highly impossible to find out the similarity between the two data points. And that's the biggest issue. And that is called curse of dimensionality. So when you increase the dimensions, it is very difficult to find out the similarity between the things. Then again, we have computational issues. If you have large amount of dimensions, then definitely any machine learning algorithm, since it utilizes all the numbers that you have given to it. Sorry, given to it. So because of that, it is quite possible that you may not be able to support it. So we want to keep attributes as low or as less as possible. Is there any question? Okay. I think I can continue. Yeah, challenges with the model. So when you have certain models, then we have certain challenges also with the models. If any one of you has some doubts or something, you can ask me or you can interrupt me if you have any. Because I don't know this Teams. Anyone else can also help me identify whether somebody wants to ask anything.
Sure, sir, we will do.
Okay, so we are continuing with the challenges with the model. So when we are looking for the model, so some mathematical thing is there, mathematical object is there, and we want to train it. We want to tell it, okay, this is the case, this is the case. So we are giving some information to it. And because of that information, it is trying to learn from that information. But when we see the learned model, then it has certain issues with itself. One of them is overfitting. What does this overfitting says? The overfitting refers to a very simple idea that your model works very well with the training data that you have fed it. But when you give it to the new data, it doesn't work. So here comes the overfitting because you have taught the model a lot on the training data. And while teaching this model on the training data, you forgot about its experiences on the unknown data or unseen data, which it has not yet seen during the training. And to avoid this, there is something called generalizability. Generalizability and overfitting is actually contrary or contrasting things. Generalization says that the model's ability to adapt properly to new or previously unseen data. So what we are looking for, we not only wants to avoid the error on the training data, we also wants to avoid error on the unseen data. But let us try to see this particular phrase, drawn from the same distribution. So when we say that same distribution, it is talking about the probability distribution. So soon we are going to talk about the probability distribution as well, and we'll look at what is the probability distribution. But the idea is we are looking for the data. We want the performance on the unseen data should be good. And how we infer or how we get this unseen data, how we can quantify our generalization ability, that is something which is important to know. And this data should be generated from the same distribution as that one is used to create the model. So the training data you have generated or you have got from some distribution, the same distribution should be used to get the test data as well. It may be different, but it should have the same distribution. So the question is, what is probability distribution? What is distribution? So consider a population of 100 people. And if we have this 100 people and we want to consider their height. So let's just see this particular problem. So here we have certain people. So this is the serial number and these are the height of people. And I have made certain low limit and the upper limit. So between 3 feet and 3.5 feet, how many people are there? 0. 0 is the frequency. So I have taken 100 people out here. I have taken 100 people out here. And with those 100 people, I want to find out what are the how many people are there between 3 and 3.5 feet, 3.5 feet and 4 feet, and so on and so forth. So this is the frequency. If I divide it by 100, I'll get the relative frequency or the possible estimation of probability. So this is a probability. This is called distribution. The height distribution of this sample. So I hope you are getting my point of understanding the distribution. The distribution is actually the relative frequency chart. So you can see here, this is the relative frequency chart. Frequency chart. So the height with this much between 4 and 4.5 is 17 people are there. So 17 people are there which are having the height between 4 and 4.5 feet. So if you draw this, this is called distribution. Naturally, what has happened when we read about it in mathematics, we see that distribution is something which is already known. No, like normal distribution or uniform distribution. You can also have a generic distribution, a natural distribution. The natural distribution you can actually estimate by collecting the data. So if you collect the data, this distribution you get. And the idea of saying that the same distribution, it means that this particular distribution must be followed. So if you are taking the test data, so the percentage of test data from the height between 4 and 4.5, 4 and 4.5 should be proportional to 17 or should be proportional to 0.17, right? So if you want to take 1,000 people, 1,000 data points as your test samples, so around 170 people must be in between 4 and 4.5 feet height. So that's called the distribution. Let's go back. Similarly, this is a distribution in the univariate probability distribution because you just have one variable, that is height. You can have bivariate probability distribution. Similarly, you can have multivariate probability distribution. In case of a bivariate distribution, you have two variables. Let us suppose with heights, along with the heights, we also have weight. So if you have two variables, it's a bivariate, three variables, it's a trivariate, and multiple variables is multivariate. So you can always have multivariate distribution. In case of, uh, you know, you can actually think the probability distribution to solve these problems. How to test a Mars Land Rover facing the sandstorm environment on Mars in prior to its reach. We have not yet reached to the Mars and we still want to know what kind of sandstorm or how the sandstorm will affect Mars Land Rover. So maybe it is of very good height, and if it is of very good height, so there is quite a good chance that the upper part of it will affect differently, the lower part of it will affect differently. So how should I understand it? How should I study it? So we try to use these distributions because we already know from our telescopes and all radars and everything. We know that how big sandstorms are there, what kind of speed of those sandstorms are. So on the basis of that, we can actually simulate the distribution, the velocity of the sandstorm at different heights. And since we know that, we can actually simulate this idea and try to understand how this Mars Land rover will get affected at different heights. Similarly, you can actually talk about opinion polls or exit polls, where you want to know which party will be going to win this election. And in that particular thing, you want to know how your data, how your people are distributed, how their opinions are distributed among the various variables. For example, you could have variables like religion, caste, economic background, education background, rural background or urban background, and so on and so forth. So everything needs to be considered. So every population, so you have certain population in rural area, you have certain population in urban area. So if you want to take the correct idea of exit poll or the opinion poll, you want to take the right proportion. So let us suppose if you have 1,000 people in 1,000 to 1, sorry, 1,000 to 100 ratio between urban to rural. So you need the same ratio should be followed in case of sampling, because you want to take the opinion poll to be as accurate as possible. So whenever we are actually trying to work with samples, we look for the distribution, what is actual distribution of the things, or of the differentiating parameters, describing parameters of our problem. So that's the idea about probability distribution. I hope I am clear about it. Now let's try to understand what we can do in machine learning. So there are four basic questions, four basic types of questions that are posed to a machine learning people. One is supervised. Supervised means I know that this is mango, I know that this is banana, and I want to give you more and more options, more and more uh, things, that this is mango, this is banana, this is mango, this is mango, this is banana. So if I have this kind of data, if I want to classify later on the data in terms of banana and mangoes, then yes, this is supervised learning. You are asking supervised learning. And unsupervised learning, you just want to know what are the categories, whether I can put the things into some groups. For example, uh, if you want to recommend a movie to some person, you don't want to group the movies in a certain group, because people are not only, I mean, okay, there are genres, I agree, but even with those genres, people tend to differ from those genres as well. At, at times they go into different genres. So the idea of putting them into genres is one thing, but idea about recommending the people is completely different, because people behave differently. One person only likes one particular genre, another person may like a complete pack of genres. So because of this idea, we don't want to group them as we have already defined. So in a defined case, we want to group them. We want to group them in certain way, right? So to group them in certain way, if the query is like that, if the question is like that, then you go with the unsupervised learning. So there is a lot of data and you still want to group them in certain way to exploit certain information. For example, you want to see in a mall, there are a lot of people are coming and you want to group them in certain way so as to put them discounts, or you won't give them some offers. So that could be an unsupervised learning where you can actually work with unsupervised data. You don't want to put them already in certain categories. Then semi-supervised learning. Semi-supervised learning is actually a supervised learning only just that you want to take the leverage of the data which is unlabeled. So let's which is unlabeled. So let me tell you very clearly. In most of these things, what happens is that this unlabeled data is actually utilized uh, for estimating the probability distribution. And if you are having more information about the probability distribution, you can tend to say a lot of things about the whole data. You can make a better classifier because of that information of the distribution of the data. We will see if the time allows, we will see that how this information can be exploited. And then comes the reinforcement learning. It's the today's means it's the normally a hot topic and buzzing word within the machine learning also. Machine learning itself a buzzing word, but reinforcement learning is again a buzzing word. So all the new things like auto driving or maybe helicopter, moving the helicopter autonomously, and finding out the strategy, playing games, artificial intelligent games, exploring the unknown territory. All these goes into the reinforcement learning. So let's just see some of the problems in the supervised learning. So they may try to recognize in the sense that, let's see. So they want to recognize whether the data is 0 or 1 or 2 or 3 or what. So out of these different digits, we want to recognize which is 0, which is 1. Or maybe you want to identify from images whether something is dog or a cat. Or maybe you want to identify from a text whether the text is sensitive, it is showing the sensitive emotion, or it is showing the attitude or joy, contentment, grief, rage, introspection, and so many emotions you can identify from a text or maybe from the image also. Right? So that is possible. Then you may want to recognize the faces, the emotions from those faces. So that's again an application of it. Now you can actually predict also from the supervised learning. It helps to predict your stock market. If you want to predict house pricing, stock market uh, values, or you want to assess the risk. If you want to plan for a premium or insurance company, you want to identify how much insurance I should ask for, a premium I should ask for. So all these things goes into the risk assessment, and the risk assessment can also go into the prediction. And we have unsupervised learning. So unsupervised learning are a lot is there. So we can cluster the data. We have certain data, and you can, even if I put them in same color, you could have identified that these things are in similar in certain way with whatever descriptions they have defined, because you can see that they have been defined in a two-dimensional space. So they have certain x2 direction, they have certain x1 direction. So this point is away from this point by a certain movement in the x1 direction and certain movement in the x2 direction, right? So they have a certain difference. So, but in these x1 and x2 spaces, these data points are similar in some way. These data points are similar. These data points are similar in some way. So this is called clustering. Then you can um, suggest your friends in the social network. That's also possible by clustering the things. Now you can also reduce the dimensions. You want to know whether which particular dimension is much informative. So this category also falls into the unsupervised learning. You want to look for the dimension which actually captures the most information. So you can see if I project all the data points onto U2, most of the data points actually collide. They will have a small distance among each other. If you project all the data points on U2, the data points will have definitely very low distance among each other. While if I project along U1, they will have little larger difference. So U1 is a better dimension if I want to project this two-dimensional data onto a one-dimensional data. So this kind of problems are also solved in unsupervised learning. Then we want to estimate the density where the cluster is dense, where the cluster is sparse. So these density estimations are also falls into the category of unsupervised learning. And semi-supervised learning. So we want to take the advantage of vastly available unlabeled data, because labeled data actually requires human effort to label it properly. Reinforcement learning. For reinforcement learning, I just want to show you this video. I hope you will be able to listen the audio of this video as well.
On Earth, this natural selection and competition led to the evolution of increasing.
Is it audible? Is it audible?
Sir, it's audible, but its volume is quite low.
Volume is quite low. Okay. Let me try it. I can do something. Just I'm removing the share and share it again.
On Earth, the simple rules of natural selection and competition led to
Yeah,
the
it's audible now.
Okay.
evolution of increasingly intelligent life forms. Today, we ask if comparably simple rules and multi-agent competition can also lead to intelligent behavior in a new virtual world. These agents are playing hide and seek.
Let me just tell you about this particular problem. That's a hide and seek problem. So the red people are seekers and the blue people are hide. They have to hide themselves. And there are certain blocks that they can utilize uh, to block the ways from which these red seekers come into and seek these blue people. So the idea with the reinforcement learning is to explore the different actions. So at any point in time, they have certain actions available in their hand. They try one or the other action and try to find out, try to uh, figure out what strategy should they make so that they can win. So the red people will have a certain, they have to, their goal is to find out the uh, blue people, and the blue people have the goal to hide themselves. So they are learning from each other. So they play a lot of games, maybe billions of games they will play among each other. And slowly and slowly, they will make some strategies. And these strategies are uh, learned through programmatically. So you need not to program it uh, from your side. You need not to say certain strategy from your side. They themselves identify the strategies. So let's see this particular video. What kind of strategies these researchers have found when they did the reinforcement learning on this small hide and seek game.
These agents have just begun learning, but they've already learned to chase and run away. This is a hard world for a hider who has only learned to flee. However, after training in millions of rounds of hide and seek, the hiders find a solution. The hiders learn to use rudimentary tools to their advantage. By grabbing and locking these blocks, they can create their own shelter. The seekers are locked in place for a brief period at the start of the game, giving hiders a chance to prepare. Even so, the hiders must learn to collaborate, accomplishing tasks that would be impossible for any single individual. The hiders are not the only ones who can learn to use tools. After many generations of failing to break into the shelter, the seekers learn to jump over obstacles using ramps. However, after many millions of rounds of having their shelter breached, the hiders learn to take away the primary tool the seekers have at their disposal. Note that we did not explicitly incentivize any of these behaviors. As each team learns a new skill, it implicitly changes the challenges the other team faces, creating a new pressure to adapt. We've also put these agents into a more open-ended environment, randomizing the objects, team sizes, and walls. In this world, they learn to construct their own shelter from scratch, requiring that they arrange multiple objects into precise structures. To prevent seekers from using the ramps, the hiders move them to the edge of the play area and lock them in place. We originally believed this would be the final strategy that the agents learn. However, we found that after more training, the seekers discovered that they can jump on top of boxes and surf them to the hider's shelter. In the last stage of emergent strategy that we observed, the hiders learn to lock as many boxes as they can before constructing their fort in order to defend against box surfing. So how do agents acquire these skills? They're trained using reinforcement learning, an algorithm inspired by the way animals on Earth learn. The agents play thousands of rounds of hide and seek in parallel for many days. They train against each other as well as past versions of themselves using an algorithm called self-play. Coevolution and competition on Earth led to the only generally intelligent species known to date, humans. While this world is far less complex than Earth, we have found evidence that simple rules can lead to increasingly intelligent behavior from multi-agent interaction. We hope that with a much larger and more diverse environment, truly complex and intelligent agents will one day emerge.
So that's about reinforcement learning. However, there are a lot of other videos that you can find from Stanford and OpenAI. You will see that there are a lot of work is going on in reinforcement learning, especially because we are looking for space exploration. We are looking for exploration in the areas where humans cannot go. So all such things where humans cannot go or humans cannot actually understand. So simulations are the only way to learn from for such things. And when we have simulations, we have reinforcement learning to be there so as to understand it, how to learn or how to make strategies for the things that we cannot do that frequently. For example, I cannot do, maybe I cannot dive into water a lot of times. But if I have a chance to dive thousands of hundreds of thousands times, my diving will be better, right? So the same thing is here. So you are providing a lot of chance to the computer or to the algorithm to strategize itself, to make something or some skill to itself. So that's the idea about reinforcement learning. So cycle riding is an example of reinforcement learning that we actually utilize ourselves to understand how to ride a cycle. Autonomous driving, we can have chess playing. All these can be actually fall into the category of reinforcement learning.
On Earth, the simple rule.
So let us try to understand how this data and the features and the distance actually help us. So we have already talked about that that we have certain attributes to define a particular thing. And then we said there is distance, which is a crucial role player when we find out the distance between the two things. And if it is large enough, then we say they are distinct. And if it is not large enough, then we say that it's similar. Now, what this distance is actually referring to. So let's try to understand with a particular problem called iris plant dataset. So you can actually download it from UCI machine learning repository. This is iris dataset. And this iris dataset is having 3 different flowers. So it has a description of these 3 different flowers: iris setosa, iris versicolor, iris virginica. So let's try to see and understand what this data set actually means. This is called petal. So this petal is the flower leaves, flower's leaf. These are petals, and there is a point of sepal. So in case of rose, if you see that green bud, which is at the lower side of the flower, is called sepal, and the red things are called petal. So we have 2 things, petal and sepal. So for both of these 2 things, we have actually calculated the length and the width. And that's how we have described a particular flower. So sepal length, sepal width, petal length, petal width. Now, if you suppose you want to look at this is some centimeters, this is also some centimeters, this is also some centimeters, this is also some centimeter, right? So now if I take 2 flowers, if I have taken the description of 2 different flowers of iris, maybe it is setosa, versicolor, or virginica, then it is quite intuitive that the sepal length and sepal width of the 2 iris setosa, same class flowers, will be almost same, right? So which means that the difference between the sepal length, the difference between the sepal length of the 2 flowers will be very low, right? Similarly, sepal length, width, difference of sepal width of the 2 flowers will be very low. Similarly, for all other things. And if I know that, then I get the similarity measure. I get this distance. This is the Euclidean distance. The Euclidean distance, what it does, it says that you subtract sepal length from the sepal length of first flower from the second flower. Similarly, sepal width of first flower subtracted by sepal width of second flower, and so on and so forth. You square them up, you sum them up, and you take the square root, and that's the Euclidean distance. Now, if I calculate this Euclidean distance, and if it comes out to be nearly 0, then definitely almost the sepal length is same, almost the sepal width is same. Similarly, petal length is also almost same, and petal width is almost the same, right? And that's the idea. So we have taken some features, and with those features, with those attributes, we are saying that they are relatively, or they are at low distance. And since they are at low distance, we may say them same, similar. That's the basic idea about any kind of machine learning algorithm. So you have the description of sample. So let's just try to see. We want to map this particular problem into mathematical problem. So this is the data. You definitely will be able to appreciate that these data points will be falling into one class, and these are making some other cluster when they are described with this x2 and this x1. So I'm describing this data with the feature x1 and x2, and with that particular thing, I am able to say that these data points are similar in certain way, and these data points are similar in certain way. Now, every data point, for example, this data point, this is 0.95, so x is 0.95. So this is this point, x is 0.95, and this is minus 1.56. This is the point which is I'm looking for, and this point is actually telling, or this is described, this plotted point is described by this thing, right? So mathematically, we see the data in this form. But when we plot it, we can see this form. This is unsupervised data because you are not looking at different classes. I'm not saying that this is +1, this is -1. I'm not saying that. I'm just saying that this is the whole data. But you see that certain data points are away from each other. So the distribution of the points are either here or here. There is not much distribution in between these two classes or between these two clusters. There is very low or no points that are falling in between these two clusters. And that's the unsupervised data, right? So objective is to group the samples on the basis of some similarity. So in case of unsupervised problem, we have this particular objective. So we want to find out some similarity. We want to group them in certain way. But if I have a class to it, let us suppose if I say that this is of circle class, this is of a star class, then this is a classification problem. Now I can say that I already know that this is belonging to the circle class. I already know that this is belonging to a star class. So I have given them names already. And I want the output in these names only, whether it is a circle class or it's a star class. But generally, since in mathematics we do not deal with the circles or stars, we put them a +1 or -1 sign, 0 or 1 sign, 1 or 2, something like that. So we give them some number which is different from each other. So maybe this class is -1, this class is +1, or maybe this class is 1, this class is 2. This is supervised data, and this is the problem wherein we want to solve we want to tell whether this diamond will fall into which particular class, whether it will fall into the circle class or whether it will fall into a star class. That's the question that we will be posed to answer. Okay, so we have already changed it to +1 or -1. That's how we have. Now, how we make our objective of machine learning in a mathematical terms, or how we can map into mathematics. So we have to identify the new data, the out of sample data. New data means that the data that we have not seen in the training. So that data we want to take and we want to put it into a certain class. That's our objective. So this is the kind of data that iris data has. So this is the description of one flower, and this flower is of type iris versicolor. This is another description of another flower, and this is again iris versicolor, and so on and so forth. And we want to find out what is the label corresponding to this. We want to associate this X to this Y. So idea is to associate the X with Y. So we want a function f that takes this description X and converts it into Y. That's the thing that we want, and that is called function approximation. Because we want to have a function which may not be the correct function. Why there is an approximate sign? Because we may not be able to identify the correct function, the exact real function. We are not able to identify, we may not be able to identify. But this function may be as close as possible to the original or to the real function which should be there, which actually maps this value to the iris versicolor, virginica, or setosa. So that's an out of sample data, and we want to map it to Y. So let's try to look at the simplest idea. We want to associate the input description to the output uh, or the class label. And the idea is very simple. Basically, we are looking at the k nearest neighbor. That's the simplest algorithm of machine learning. And from this particular image, you may be able to identify what is the problem or what is how you can do it. So it looks at the k samples that are most near to the sample that is newly taken, or that's the test sample. So that's yellow is the test sample, and you want to predict about it whether it will fall in class A or class B or class C. So to find out, you take 6 data points that are most near to this particular yellow data point. Once you find out that, you just take the vote. So there are 3 from class A, there are 2 from class B, and there is 1 from class C. So definitely 3 class is the winner class. So this yellow data point will fall into the class A. That's how this k nearest neighbor can work. But can we think a little bit different? That could be very simple way, but uh, this algorithm can little bit changed. You can see that if I go for the k nearest neighbor, what I need to do, I need to calculate the distance of this yellow data point from each and every blue point, and each and every red point, and each and every green point. And then I have to sort it, the whole thing I have to sort, and then I have to take first k elements from the ascending sorting. I have to take first k elements, and out of those first k elements, I have to take the classes. I have to note down the classes, the count of classes, and accordingly, I have to put it into one particular class. So the idea is, can we think about something different which can work in a similar way, but maybe faster or something like that? So there is another algorithm. However, it is not named algorithm, but this can also be chosen as one of the ways to find out the similarity. The idea is, you just take a hypersphere in the dimension that you want, and you look whether the data points fall into that sphere or not. Which class is most likely in that particular sphere? So in this particular case, if you consider this particular sphere, the 2 red data points are there. So this green test data point can fall into the red class. But if you consider this bigger circle, then definitely you may be likely to say that it might be falling into the blue class. So that could be one of the ways you can also think about changing the nearest neighbor into different ways. The whole sole idea that I want to convey here is that the similarity measure is the one of the most important ideas that the machine learning uses. Similarly, you can also say that if you take any, if you have x at your hand, and if there is another x which is, let us suppose, one distance away, then this much is the similarity score. So you take the distance and you associate, if the distance is a particular value, then you associate with that particular value a similarity score. And you can take the weighted average to find out the output. And this idea you can use for regression as well, right? So, regression means you want to predict a value. For example, if you want to say you want to predict the house price, then it will be a continuous value. It will be a real value. So if you associate all the data points, the similarity measure, so the whole training data has some or other similarity measure. And this with this similarity measure, you can take that value, you can multiply with that. What is the class of that? What is the output of that? That particular weight, you can take it from this similarity score. And once you take the weighted average of it, you will get to know the predicted value of at X. What is the predicted value of at X that you can get? So that's how you can actually utilize k nearest neighbor or the similar to k nearest neighbor algorithms for regression as well as classification. So what's the idea about k nearest neighbor? The k nearest neighbor is very easy, highly intuitive, because you have the training data. You just have to find out the nearness of that data point to the existing or the training data points. The only thing that is actually important is k. You don't know what should be the k. What is the ideal value of k? And we know this ideal value of k by tuning it. We try to take different values of k, try on that, try to find out whether what is if this value if I take, if that value I'll take, then how the performance of my classifier will be on the validation data. The validation data is the data which is not taken into the training part. So if you have the data, complete data, you separate it out in the two sets, the test data and the train data. So if the model is performing well on the test data as well, then you say it's good. If it is not performing on the test data, it may not be that good. You can actually look for different k. So that's the idea about tuning the parameter. Again, you can notice that there is no training in this particular k nearest neighbor, right? So you have all the data, it is there with you. As soon as a test data comes, you try to take the distance from each and every data point already in the training data. So that's a lazy learner. And we know that the whole data is required during the prediction. So the memory requirement is high. So one thing I want to know, I want you to notice with this particular graphs. This is a k nearest neighbor, and this k nearest neighbor is with 1. K is equals to 1. This is k is equals to 3, k is equals to 7, and so on and so forth. You can see here what is happening. When I take k is equals to 1, there are very small regions are there. So this decision boundaries are really very complex. Complex in the sense that if I take a small change in any of the at any data point. So for example, if I have a data point within this particular blue space, and if it takes a small error, so let's suppose it shifts from here to here, then your class changes. So it is very much sensitive to the noise. If I add certain noise in the data, it will be falling into some other region, some other class. While if you look at this particular thing, it is not that much problematic. You can see this is relatively, this is saying, okay, if you add in most of the data points, if you add certain noise, they will remain in the same region. But here in this particular case, it is very sensitive, because in most of the data points, if I many of the data points, if I put some noise, then they will go into some other class. So this robustness is required with any classifier, and that is called the degree of generalizability. So we are looking for the generalizability because of this thing. And you can notice that with the k nearest neighbor 1, k is equals to 1, this is overfitted. Overfitted in the sense it will work on the training data 100% accurate. Why? Because if you have training data with you and you take the data from this training data only, and you want to ask whether the most near neighbor is what. So it itself is the most near. And since it is most near to itself, and we are looking just with the k nearest neighbor, the same class will be reported. And hence, the training data, with the training data, one nearest neighbor will give 100% accuracy. But then, when we talk about robustness of this classifier, it will not work. It will actually switches the decision very quickly with a small error. So that's the problem. Now you can see here, when we take a large number of k is very large. Now you can see that slowly and gradually k is very simple, becomes very simple. Very simple means it's too simple. It's not actually taking the advantage of the local information available. And since it is not taking the advantage of the local information available, your accuracy on the test data is actually not helping you. It's not getting better. And in this particular case, whosoever wins, whatever class wins in the final, if one particular class has 51 samples and other class has 50 samples, then the whole region will be classified to the only red class. So if the red class has 51 samples and all other class has 49 or 50 samples, the red class will be all everywhere. So you are not taking any advantage of the local behavior. So we have to lie between these two things. We cannot be oversimplified, but we cannot be overfitted. Let's take the same idea on a different data. Now the problem is, now we don't have class. We don't have a class available to it, but we want to see whether we can cluster them in certain way or not. So when we do this, we are looking for iterative ideas. Why? Because when we go with the iterations, small changes, then there's quite a good possibility that we reach to a better option rather than going in just one way. What does a k-means clustering does? What it does actually, the problem is like this, that you need to cluster the data. So you have a lot of samples available with you, and you want to put them into groups. Now, if I know that how many groups I have to group into, let that be k. So if you know already that what is k, how many groups you have to make, so that k you have to take. And what you can do, you can actually randomly choose k data points out of that particular pool of data. Now, if you take those k data points, you can use them as centroids. Centroids means they are the cluster centers. If you choose them as a cluster center, you can ask every data point whether they are going with that particular cluster or some other cluster. So whosoever is nearest to that particular cluster will come into a particular cluster, and others go into the nearest clusters, their own nearest cluster heads. In that way, we actually make a cluster again. We then again find out the centroids. Once we find out the centroids, we again recluster. Centroid is nothing but you can take the average of all the attributes of the samples falling into one cluster. So if I have taken one particular data point, so for example, if I take I want to take one. Let us suppose if I am looking at this particular thing, and if I choose this data point as one of the cluster head, and maybe this data point is one of the cluster head. So I will choose all those data points which are nearer to this cluster, and which are nearer to this, I'll make another second cluster to this. So Once I have made this entire cluster, whichever is nearer to this falling into this A1 cluster, and whichever is falling nearer to this will be falling into its cluster. Once we have made some cluster, we'll take the average of all the data points and we'll make some other cluster head or centroid. So let us suppose our centroid is shifted here, and in this particular case, maybe shifted here. We again do the same job. Whosoever is nearer to this particular data centroid will be falling into cluster 1, and whosoever will be falling near to this will be falling in this particular cluster. So we do iteratively this particular exercise, and once we are done, or once we get some good performance metric, we achieve some good performance metric, we stop it there and we say that the clustering is done.